So, good afternoon, everybody, for our 17th edition of the Code of the Month. Today we have the pleasure to have as speaker Peter Donnell from the CoE EoCoE, energy-oriented CoE, and he will present his work on Gisela, a code for simulating fusion reactors. So the stage is yours, Peter.
Okay, thank you. So hopefully now you should see my screen.
Yes.
Great. Why I see. Okay, now it should be full screen. Okay.
Yes.
Great, thank you. So good afternoon, everyone. So I'm Peter Donnell, and as was introduced before, I'm working at CA Cadarache in south of France. And here we are working on simulation of turbulence in Tokamak plasma. So I will start by giving you a general context on what we are doing in our lab and what are the goals we have. Then I will present you the current version of the Gisela code and our roadmap for the future. So the upgrades we need to do on our code to target exascale simulation before concluding. So for those of you that are not familiar with fusion, I prepared a few slides to give a bit of context. So first, what you need to know is to sustain a plasma without external heating. You have to compensate the loss, which can come from different physical parameters, like turbulence or just diffusion and so on, by the fusion power, which is generated by the fusion reaction. And doing a simple calculation, you can really derive a criterion for having this self-heating to be higher than the loss, which is equivalent to having the triple product of the density times the temperature times the energy confinement time, which is above a given threshold. This threshold is actually depending on the fusion reaction we are considering. And the simplest to have on Earth is the fusion of deuterium and tritium, which are two isotopes of the hydrogen, that generates helium helium atom and a neutron, and release more than 17 mega electron volt per reaction. So this extra energy is actually splitted respectively with the mass of the two components. So 20% goes to the helium, and actually this helium can interact again with the plasma and so heat the plasma. And 80% of this energy is transferred to neutrons that basically do not see the plasma and go straight to the plasma wall, or the device wall, sorry. And so you need to take the energy of these neutrons for the energy production, and also to regenerate tritium via some reaction that I will not discuss today. So now let's come back to this criterion of the triple product. Actually, the temperature, the optimal temperature is dependent on the fusion reaction you want to do. And we know already in advance that for this deuterium-tritium fusion reaction, the optimal temperature is of the order of 150 million degrees. So on every lab where we want to perform fusion, this is more or less the target temperature. And so you have two strategies to fulfill this criterion. Either you try to increase the density or the energy confinement time. And this is, it leads to two strategies. So you have what we call inertial fusion, where you have a small target of deuterium tritium, which is actually heated by some lasers that are represented here in blue. They heat what we call a holochrome, which is a cylinder. I think it's in gold. And then with this, you have a transfer of energy between the lasers as X-rays, and these X-rays are then hitting the target, which is this small white part here. And in 2022, there was a record in the National Ignition Facility in the US, where they managed to have more fusion energy released compared to the X-ray that are used to hit the target. So it was a historical physics result. But unfortunately, even though there are a lot of progress, let's say this last decade on this technology, we are still quite far from energy production for two reasons. First, in terms of energy, what you need is not the fusion energy to be larger than the X-ray, but the fusion production to be larger than the grid. And with the current technology, we are still two orders of magnitude lower than the grid energy that has been used to generate the lasers. And another drawback of this technology is the repetition rate. I think right now they managed to get to one shot per day, and to have let's say reasonable electricity production, it should be 10 Hertz. So against orders of magnitude too slow. And then you have another strategy, which is now targeting an increase of the energy confinement time, and it's what we call the magnetic confinement approach. And you might have heard about the ITER project, which is one of the largest scientific projects of mankind history, which is under construction in the south of France on the Cadarache site. So this is a huge site. Actually, my lab is just outside this site, somewhere here. You see this site is really huge. Just to give you an idea of the scale, this building, so like this, is 60-meter high. So it's really huge, and it's actually the place where we have what we call the Tokamak pit, so where the Tokamak will sit. And all the rest is assembling parts and also power supply and so on. And to give you an idea of the scale, this is the Tokamak, the ITER Tokamak, and here you see one guy, a normal guy, just to give you the scale. Okay, because ITER project is really huge and costs a lot, we have to prepare its operation even before it's starting to work to minimize the risk of problems and to optimize the performance of the plasma that will be generated in ITER. And to do so, we need to have a complete chain of numerical tools ranging from scale models, which can be used in real time, to first principle simulation, which are much more costly, but also more valuable. And today I will speak to you on one of these first principle simulation code. Another part which is needed for you to understand this presentation is that in Tokamak plasma, the transport is mainly governed by turbulence. So it's, if you want, small scale fluctuation of density, temperature, and the electric potential. And the Tokamak plasma has specificity that they are weakly collisional due to their really high temperature. And so they cannot be described by a fluid approach. So we need a kinetic approach. So a priori, we should go in 6 dimensions. Fortunately for us, the turbulence is at relatively low frequency compared to the gyro motion of electrons and ions. And so we can do what we call the gyro average of these fast scales. And with this, we end up with what we call gyrokinetic theory, which allows to reduce the phase space from 6D to 5D. So it's already a gain. And we can increase the time step to only describe turbulent scale and not the gyro motion scale, which would be faster. So now let's go to the Gisela code, which is the unique gyrokinetic code based on Simulink-Longchamp scheme. It's written mostly in Fortran 90 with a bit of C modules, and uses an hybrid MPI OpenMP parallelization to run mostly on CPUs, even though we start to get to GPUs with this code. The development started more than 20 years ago, and it's a collaboration between physicists, mathematicians, and computer scientists. This collaboration is mostly in Europe, but now in the last 2 years, Singapore colleagues joined the project. Just to give you flavor of what we are doing in the last 10 years, is to increase the complexity of the physical model we simulate. So for instance, we went to a situation where we were not describing the electron response to now a case where we describe the electrons. Then another example is we went from circular cross-section, so like this one on the bottom, to what we call shaped plasma, so with something like an elongation and a triangularity on the plasma shape. And we increase over modules, let's say the reality of these modules. And now it allows to have more physics inside. But of course, because the complexity increased, the numerical cost of the code increased accordingly. And so we always try to improve the numerical efficiency to compensate the increase of complexity due to the improvement of the physical model. And just quick illustration of this strategy. For instance, in 2021, 2022, we make a lot of effort to vectorize more the code, to optimize cache, and to have asynchronous MPI communication. And thanks to this strategy, we have a gain of more than 70% on the execution time on the same simulation input. So it was a good success. And with this exactly the same version of the code, we performed a weak scaling on one of the supercomputer in France, CAHF, which at that time was, I think, if I remember well, in the top 10 worldwide. And we got access to the full size of the machine. So it was the first time we had access to so many nodes. And here you see the relative efficiency as function of the number of nodes. So in plain line, it's the efficiency without the I/O. And you see that up to, let's say, 4,000 nodes, the efficiency stay quite high, more than 80%. And then when we reach the size of the machine, we start to decrease. I think it's really due to the size of the machine here. But at that time, we identified that when we add I/O, they don't scale as the rest of the code. So we already at that time identified that I/O was one of the major issues to go to exact scale. So that's one of the reasons we decided to change the strategy. And then, sorry, let me come back to prepare exascale simulation. We had to change a bit the strategy compared to what we have up to now. So just let me explain you why we really need exascale simulation. So as I told you before, the transport in Tokamak is mainly due to turbulence. And so it's intrinsically multi-scales. Indeed, the turbulent structure are proportional to what we call the Larmor radius, which correspond, the scale I'm mentioning correspond to this small fluctuation here. And we need also to model the full plasma, so which is proportional to this what we call minor radius. So it's the width of the plasma. And so the grid resolution, if you just want to describe in a 2D this turbulence with a good resolution, the grid resolution has to scale as what we call rho star to the power of -2, where rho star is basically the ratio between the Larmor radius and the minor radius, so the size of the Tokamak. For the West Tokamak, which is the largest Tokamak in France before the ITER is in production, rho star is the order of 250. So actually it's rho star to the power of -1. And for ITER, it will be basically 4 times this value. And so it means that just to resolve this 2D plane with the turbulence, we need to increase by a factor of 16 the grid resolution to go from a West case to an ITER case. And already for a West case, we needed 10 to the power 11 points. So it's starting to be a really huge number of grid points. So that's for the spatial scale. And actually, we have more or less the same that appears on the temporal resolution because the correlation time of turbulence, so what we need to describe temporally, scales like the cyclotron frequency. Whereas we need to actually simulate the confinement time, which I mentioned at the beginning of the presentation. And so the number of iteration needs to be the energy confinement time divided by the turbulence times scale. And again, this number of iterations scale like either rho star to the power -2 or rho star to the power -3, depending on the physical regime we are in. And so it means in terms of number of iteration, you have to increase by a factor of 16 to 64 to go again from West to ITER. And last point, the numerical cost for one well-resolved simulation of West is of the order of 10 million of CPU hours. So you already see with these numbers to simulate ITER with what we have right now, it's impossible. And so that's why we decided to develop a new code called Gisela X++, which is more or less a rewriting of Gisela, but using modern C++. And then for the parallelization part, we will use MPI and CoCoS. CoCoS allows to have portable code, which is compatible both with CPUs and GPUs natively. More on the, let's say, new features we want also to do while developing this code. We want to have what we call non-uniform mesh, because we have really large gradients in the edge of the plasma. Maybe if I come back here, here the edge of the plasma, you have really large ratio of maximum to minimum temperature, and the same for the density. And so to describe this, we think we need a non-uniform mesh to avoid to increase too much the number of grid points. Then we need to describe what we call X points. So it's a particular place in the magnetic topology where the polyidal magnetic field goes to 0. And because of this specific magnetic topology, it's actually quite hard to describe numerically this 6 points. So there is a development dedicated to describing the plasma around these 6 points. And lastly, something I didn't mention up to now, the Tokamak is the most mature geometry for, let's say, magnetically confined plasmas. But there is an alternative, which is called Stellarator, which is shown here on the plot, where the magnetic topology is intrinsically 3D. And so we also want to describe in the long term this kind of plasma. And finally, among the criteria for this new code, we want to have scalable I/O, because I showed you that in the Fortran version it was not possible, and also in situ diagnostics. So the development of this new code started a bit more than 2 years ago, and is supported by multiple projects and collaboration, mostly in Europe. So here, EoCoE is one of the projects we are in, but there are also many others. And so now, because we started 2 years ago, we start to have something which becomes interesting. So the strategy we adopted was to create a modular library in C++, which uses libraries that are either not related to the Fusion community, like DDC and PDI for both strong typing and I/O, or also Ginkgo, which is linear algebra. And we also translated some modules that were developed only for the Fortran version in C++, and that's the case for the collision operator. And in all of this, we use CoCoS natively. So we put all this in our library, which is called Gisela lib++, and then we also added some mathematical tools that will be useful for our plasma simulation. And the goal is then to create different applications that will rely on this library. So here you have a list of 5 potential applications. the two in dark red are already available or close to be available, and the three in light red are what we plan to do in the next future. So now I will show you results obtained with the two versions already available. But first, just to tell you that it's really European collaboration among people in France, in Germany, and in Switzerland, and also some people from Singapore more on the physics part. So let me show you a bit more results on the first application we developed with this library. It's a 1D, 1PK, so if you want, there are 2 dimensions in the system. And it's supposed to describe the plasma along one magnetic field line. And actually, I will not describe all this. What we can focus on the left-hand side plot, where you have the time to solution as function of the number of points in the simulation domain, and both for CPUs and GPUs at the bottom. And in both cases, you see that we are close, or at least at the low number of grid points, we are close to the perfect scaling, and then in some cases we start to have a bit of deviation to the perfect scaling, but it's already a huge simulation. So for 2D idea. So we were quite happy with this simulation performance in terms of numerics, and so we increase the size of let's say the number of dimensions to start to have something bigger. And so we went to the same kind of equation, but in 4 dimensions. And then we had to include MPI to be able to use multiple nodes. And that's what is represented, especially here on the top right figure, where we compare 3 type of architecture. So in blue, it's Genoa CPU nodes, and then in red and yellow, it's 2 types of GPUs. So in red, it's AMD, and in yellow, it's NVIDIA GPUs. And we see that, of course, CPUs are slower than GPUs as expected, but we think we have quite good scaling, even though this code has not been optimized yet, because we want first to add the 5th dimension before doing the optimization effort. But already it's a really good sign that everything is working as we expected up to now. And a bit more focus on 2 features. First one is how to handle the exploits. So we decided to use what we call patches. So if you want, here the different colors are different patches here, and then we need to plug them all together so that we can simulate the plasma around 6 points. And we have, for our set of equations, we have 2, let's say, challenges. One is more on the semi-Lagrangian advection across these patches. And actually, I will show you in the next slide where we are on this. And the second difficulty is to solve the Poisson equation, so if you want the electric potential on the whole device, so across all these patches. And then here we have different approach to do so. So some people are working especially on the X-point, and others are doing optimization in terms of numerics of what we already have in GCR Fortran. And so for the semi-Lagrangian part, actually we rely on strong splitting to evolve the distribution function. So we don't solve directly a 5D advection if you want. We split it in different sub-advection. And what was developed by Pauline Vidal, who is a PhD in Germany, it's a patch-wise spline interpolation to actually look at the interface. And there is a paper in archive where she show that even if you have here, in this case, 5 patches, you can actually describe quite well the evolution of one single density blob, let's say, but is crossing the different patches. Okay, I will not enter the details here. So let's go to the conclusion. So the GCR Fortran code is one of the biggest code for the up to now for the gyrokinetic community. It's optimized on up to more than 500 kilo cores on standard CPU, sorry. Usually we use a bit more than 200 millions of CPU hours per year. So we are one of the big consumers in France. But we already identified some limits to this code, both in terms of physics and on numerical efficiency. So we decided to develop a new code in C++, sorry for that, to be able to have exascale simulation. And at the same time, we added new features to the code. So for instance, the use of patches that helps to handle the large gradient, the X-point, and a bit more physics. And I thank you for your attention. I'm waiting for your questions.
So thank you very much, Peter, for this very interesting talk, which allowed at least me to learn a bit more about fusion reaction and the reactor design and the efforts that are needed to really simulate that and all the challenges associated with that. So the floor is open for questions. I thank Peter very much again. And for the next code of the month, I can already announce that we will have that on the DL2 library on finite elements. I think I have to look, 23rd of July, is that true? I think so.
Yes.
But not sure, we will send email about that.
It's 23rd of July. Thank you, okay. Thank you, Ram. Thanks, Peter, and see you, all of you, to the next code of the month. Bye.
Goodbye.
Thank you very much. Goodbye.